Hello everyone. So it's already time, but since nobody has joined the meeting yet, I'll wait for a few minutes so that if someone wants to join the live sessions, they can join the sessions and then we can discuss the beginning of molecular physics, week 9, whatever was discussed in the class, we will solve some problems based on them. Okay? So I'll wait for maybe couple of minutes to see if anybody is joining and then we can start. Okay, so I guess we have waited quite some time, and since nobody has joined, I think I will start and then you guys can watch it on YouTube. But I'm requesting to please join the live sessions. It will be helpful for both of us because then we can have the sessions to be more interactive and much better, right? Anyway, I'll upload this on YouTube, and I really hope that this is being helpful in solving your assignments and learning atomic and molecular physics. Okay, so we have come a long way and now we are on week 9. So let us start with some simple standard problems which are discussed in the class. So let me write the first one. Okay, so this is the first problem. Yeah. So this first problem is about lamp shift, which was discussed in the class, and the question asks several things about lamp shift, like what actually lamp shift is and what causes lamp shift. So if you look at the first option, it says the lamp shift is caused by Thomas precession. Okay, so and option C says that the lamp shift is caused by vacuum fluctuations of the electromagnetic field. Now, if you remember from the lectures, this was taught in the class that the correct reason or the correct cause of lamp shift is the vacuum fluctuations of the electromagnetic field. So this option is correct. What about option B, that a splitting between 1s and 2s energy levels in hydrogen? This is known as lamp shift. Okay, so what is this option correct or not? So this is incorrect. Okay, this is incorrect because it does not happen between 1s and 2s orbitals. There is no splitting between 1s and 2s energy levels in hydrogen. This is not correct. Okay. So this lamp shift, this is anomalous energy difference in energy between two electron orbitals in a hydrogen atom. Okay. So we get differing energies by the 2s half and 2p half orbitals of the hydrogen atom. Okay. So differing energies contained by 2s half and 2p half orbitals of the hydrogen atom. Okay. And this is caused by interactions between the virtual photons, which are in fact created through this vacuum energy fluctuations of the electromagnetic field. Okay. So another interesting thing is, so why this lamp shift is important, because it plays a significant role through vacuum energy fluctuations in theoretical predicting of Hawking radiation from black holes. So we can link the Hawking radiation with this lamp shift, and then we can predict black holes, the Hawking radiations. Okay. So let's go to the next one. So the next question is, what is the total magnetic moment of an atom in the 3p0 state? So this is the second question. And the question is that what is the total magnetic moment of an atom in the state 3p0? And the question also asks us to not consider the contribution due to the nucleus, because as we know, nucleus also has a spin, like it has protons and neutrons, which are spin like fermions, and they have spins, and they can also have their magnetic moments, which can contribute to the magnetic moment of an atom. So the question clearly asks us to not consider the contribution from the nucleus, only from the electron. Okay. Now for an electron, they ask us the total magnetic moment. Okay. So total magnetic moment. So this will come from two parts, right? So one will be because of orbital motion, and another will be because of spin. So this is L and this is S. So total will be because of our total angular momentum J. Okay. And total angular momentum J, and the quantum number corresponding to J is small j, like here L and here S. Okay, so we have to find out J. Once we have J, we can write total magnetic moment let's denote that by mu. So that is given by G times mu B under root J plus 1. Okay. So once we know J, we can just plug in the value of J in this equation, find out G, and then we will have mu in terms of mu B. So first of all, the state that is given to us is 3p0. 3p0. Now what this means is, so upon comparing with general notation, and general notation is 2s plus 1, L and J, right? So upon comparing, what we get S is 1, we get L is also 1 because this is P, so SPDF 0 1, so this is 1, and finally J is 0. Okay, so this is what we are getting J is 0. Let's say this is equation 1 and this is equation 2. So upon putting J is equals to 0 from equation 2 and equation 1, we get mu is equals to 0. Okay. So our total, so the quantum number corresponding to total angular momentum is 0, and therefore we can see that our total magnetic moment will also be 0. Therefore A is the correct answer. Okay, so let's move on to question number 3. Okay, so the question asks us that which of the molecules given to us are microwave active, and the options are CO2, which is carbon dioxide, H2, which is hydrogen, HCl, which is hydrochloric acid, and Cl2, which is chlorine. So the question is asking about microwave active molecules. Okay, so to have microwave active molecule, to have microwave activity, a molecule must have a permanent dipole moment. Okay, so it must have a permanent dipole moment. Now let's look at all the options one by one. So for CO2, we have one oxygen here, then we have carbon, and then we have another oxygen here, and they are bonded like this. Okay, so because this is symmetric about its center, so the total charge distributed about the center is symmetric, so no net dipole. Okay, similarly, if we look at hydrogen, this is also H and H, and this is also symmetric about the center, so this also no net dipole. Same as hydrogen, we can also do chlorine, and again it will also have no net dipole. But HCl, as you can see, it is non-symmetric, right? It is non-symmetric. So for example, this is symmetric, this is symmetric, this is symmetric. HCl is non-symmetric, and due to difference in electronegativity of H plus and Cl minus, HCl has permanent dipole moment. Okay, and therefore option C is the correct option. Okay, let's move on to the next one. So this is a question based on Zeeman effect, and the question asks us about the Zeeman splitting. Okay, the amount of Zeeman splitting that is happening, the shift, the separation between the splitted spectra, and the options are okay. These are the options. So this problem is all about Zeeman splitting. And this problem, so very similar problem we also solved in the last session. So therefore I'm not going to derive the formula for delta lambda. In case you don't know how this is coming, you can maybe watch the lectures or watch the tutorials on week 8 course content. So this is week 9, so previous week's course content, and I'm going to use the formula directly, and the formula is the delta lambda, which is the splitting separation. Okay, the separation in the splitted spectra, this is the separation delta lambda, and this is given by EB times lambda squared divided by 4 pi MC. Okay, so here again we discussed this in the last session. Here E is charge of electron, okay. B is magnetic field, okay. M is mass of electron. C is speed of light, okay, and lambda is wavelength. Okay, so we have electronic charge, magnetic field, wavelength, speed of light, and mass of electron. So all we need to do is just plug in these values. Just plug in these values and we will get our answer. So then delta lambda becomes simply all the values multiplied together. Okay. And lambda is 5000 angstroms. So we square it. So let's write it 2 times. And then square of minus 10 is minus 20. Then you will divide it by 4 and pi. This is 9.1. And this is 3 into 10 to the 8. Okay. So let's collect all the powers of 10 together. So this is, okay, this will be 1.6 into 0.5 into 25, and this is 10 to the minus 39, and here you have 1 2 3 4 5 6, so plus 6, and then from here we get minus, this becomes plus 31 and minus 8. Okay, so this is delta lambda and this will come out in meters. So if you want to convert it into angstroms, we then multiply it by 10 to the power 10. Okay, so we add 1 10 here, just like this, and then we will divide this thing by 4 and pi and 9.1. Okay, yeah, looks good. So if this 4 will cancel out this will become 0.4 and this will become 0.5, so this will become 0.2 and into 25, so that will be 2 into 2.5, so this just becomes 5, and we divide this. Okay, let's write this as pi into 9.1, and this becomes minus 39 plus 31 is minus 8, and minus 8 is minus 16, minus 16 plus 16, so basically 10 to the power 0. So just this thing. Okay, now let's pull out our calculator. Okay, yeah, we left out 1 3 here, so this thing. Okay, That's why it was not matching with any options. Let me try again. So it is coming out to be around 0.059, roughly 0.059 angstroms. Okay, which is matching with option A. So if we write it in terms of picometers, okay, let's write here that delta lambda, so 1 2 is 5.9 picometers. So you can see that a strong field of UN like 0.5 Tesla splits the wavelength of 5000 angstroms only by just 5.9 picometers. Just 5.9 picometers, which is very, very small. Okay, so this is a very, very finite splitting that is happening because of this magnetic field. Okay, good. Now let's go to the next problem. Okay, so another problem based on Zeeman effect, very similar to the last one. So in the last one, what we were asked is to was to calculate the delta lambda, okay, which is the separation in the splitted wavelengths when we applied a magnetic field of zero point 0.5 Tesla. Now in this problem, things have changed in the fact that now the shift is to us to be 0 0.5 angstroms, and the wavelength is given to us to be 4000 angstroms, and the question is asking us to estimate the magnetic field which is causing this Zeeman splitting. Okay, so you can try on your own. In the meantime, I can have some water and then we can resume. Just give me 1 minute. Okay, so let us start solving this one. Okay, so here in this problem, the value of delta lambda is given to us, right? So here we are given minimum value of delta lambda, that is given to us as 0 0.5 angstroms. Original wavelength, that is given to us as 4000 angstroms. And we know from the equation, what is the equation? Delta lambda this is given by E B lambda square over 4 pi mc. So we can write B as 4 pi mc delta lambda over E lambda square. Okay, so this is the equation that we have now. So let's plug in the values. Let us plug in the values. Let me bring this thing here. Okay. Now let's plug in the values. So this is 4, this is pi, mass is 9.1, right? Delta lambda is 0.5 and angstrom is -10. Then we divide this thing. This is 1.6, 10 to the minus 19, and lambda squared will be 4000 times 4000 and 10 to the minus 20. So this is what we get now. So we can again collect all the powers of 10 together. So this 4 times 0.5 is just 2, so this becomes 2 pi into 9.1, and this becomes 1.6 into, and then again let's write this as 16, and then let's collect the powers of 10. So this is minus 31, then minus 10, plus 19, this is 1 2 3 4 5 6, minus 6, and plus 20. So this is the value of B which we will get. Okay, so again we can cancel out this 2 and this will become 8. So this just becomes 9.1 pi divided by, and 8 times 1.6 is 12.8, and then minus 31 minus 41, right? I again forgot one speed of light. This is 3 into 10 to the 8 here. Okay, so we will have 1 3 here, minus of 9.1, this will be 27.3, and we will have one additional 8 here. Okay, so this is minus 31 minus 41 minus 47, and this is 2039 plus 8, which is plus 47. So this is just 10 to the 0. So all these things cancel out, so we are just left with this. Now again let us pull out our calculator. 27.3 into pi divided by 12.8, and this gives us 6.626 Tesla. Okay. Roughly 6.6. magnetic field to create shift of 0.5 angstroms, right? Of 0.5 angstroms in the splitting of 4,000 angstrom wavelength is approximately 6.6 Tesla, okay, which matches the option D. So again, we see the problem of Zeeman effect. This time we calculate like what is the magnetic field which we will require to resolve the spectrum. Okay, so we were given that we have one spectrometer which can resolve 0.5 angstroms. So the minimum shift that should be there, therefore we have written minimum delta lambda, because this is nothing but resolution of spectrometer. This is resolution of spectrometer. So our minimum delta lambda has to be equals to the resolution of spectrometer, which is 0.5 angstrom. So then we just put the values in the formula, calculate, and we get roughly 6.6 Tesla. So let us solve next one, which will be question number 6, I believe. Okay, so we have two electrons which are obviously non-identical, two electrons one belongs to 3p and the other belongs to 3d. Now we want to couple their momenta, and the way we want to do it is by using LS coupling scheme. Okay, so LS coupling scheme, what happens in LS coupling scheme? So in LS coupling scheme, L is given by L1 plus L2 all the way to L1, let me write this as minus all the way up to L1 plus L2. Similarly, the S, that is given by S1 minus S2 and then all the way to S1 plus S2. Okay, where L1 and S1 belong to 3p electron and L2 and S2, they belong to 3d orbit. Okay, okay. So yeah, let us then begin. So then our L, okay. So our L1, what is L1? Our L1 is, because this is P, so SP L1 is 1, right? And L2 is 2. And S1 is half and S2 is also half. Okay, therefore our L will go from, so 2 minus 1 is 1, then 2, and 2 plus 1 is 3, and our S will go from half minus half is 0 and half plus half is 1. So these are the possible values of L and S, and now we will couple them. So let us start with S is equals to 0. So we will have two cases, that when S is 0, and our L is 1, so this would imply that our J is 1. When L, okay, when L is 2, this will imply J is 2. When L is 3, J is also 3, because S is 0 in all cases. So 2S plus 1, this is simply 1, and this is, we know, this is the multiplicity. So this is 1 for all the cases. 1, L1 means SP, this will be in P, and 1. Again this will be 1, D, 1, and this will be 1, and then this is SPD, and this will be F. Sorry, this will be 2, this is F, and this will be 3. Okay, now for S is equals to 1, our 2S plus 1 will be 3. So this is the multiplicity. When L is 1, our j will be 2, then L is 2, j will be 3, correct? And L is 3, j will be 4. Okay, so here 1 plus 1 is 2 and 1 minus 1 is 0. So actually it should be like this, 0, 1, 2. Now j minus L here is 1 and j plus L is 5. Okay. Sorry. So this will be, so L is 2, S is 1. So L minus S is 1 and L plus S is 3. Similarly, this will be 3 minus 1, 2, and then 3, and then 3 plus 1 is 4. So all these terms. Okay, so here we will have 3 terms. So 3 terms. So these are written as 3p0, 3p1, and 3p2. Similarly here it will be 3d1, 3d2, 3d3, and finally 3. This will be, here L is 3, so this will be F, 3f2, 3f3, and 3f4. So if we now, let's go back to the problem. So the problem asks how many spectroscopic terms result from the LS coupling of 3p electron and 3d electron. So if we count, this is 1, 2, 3, then this is 4, 5, 6, 7, 8, 9, 10, 11, 12. So in total, we will have 12 terms, and therefore the correct option will be C. In total, we get 12 spectroscopic terms. Okay. So this was LS coupling of a 3p electron and a 3d electron, which resulted in all of this. Okay. Let's then move on to the next one. So this will be question number 7 now. Okay. Okay, so this is our next problem which we are going to solve now. And what is this problem based on? Okay. This problem is based on reduced mass of carbon monoxide, CO. Okay, so we have kind of two molecules, carbon and oxygen, and they are bonded, right? So this is, let's say, carbon, and this is oxygen, and its mass is given to us as 1.99 into 10 to the minus 26 kg, and oxygen is 2.66 into 10 to the minus 26 kg. Okay, and now, so this is one molecule. Okay, so this is just one molecule. So this is our CO. Maybe I should draw this. Okay, let's leave it like that. So this is CO molecule, and now we are asked to find the reduced mass. Okay. So reduced mass. So if we have for a many body system, okay, 1 second. Okay, so we have to take one urgent call. So where were we? Yeah, we were talking about reduced mass, and we were writing that for a many body system of masses m1, m2, m3, and so on, let's say up till mn, reduced mass mu is given as, so this is how we define mu. Mu is defined as 1 over mu 1 over m1 plus 1 over m2 plus 1 over m3 all the way up to 1 over mn. Okay, so therefore for a carbon monoxide molecule or CO molecule, 1 over mu will be 1 over mass of carbon plus 1 over mass of oxygen. Okay, or we can also write this as mu is mc no divided by mc plus no. Okay, and now let's plug in the values. So mc is, it's written here, 1.99, 10 to the minus 26, 2.66, 10 to the minus 26, divide this by 1.99 plus 2.66 multiplied by 10 to the minus 26, and it will also come out in kg. So let's cancel out these two. Therefore we get mu as 1.99 into 2.66 divided by 4.65 into 10 to the minus 26 kg. Okay, so again let us calculate. So 1.99 times 2.66, this is nothing but 5.29, and we have to divide this by 4.65. So this comes out to be 1.138 to 10 to the minus 26 kg. Okay, let's see if it is matching. Yes, it is matching with option B. Okay, therefore the reduced mass of CO molecule is 1.138 times 10 to the minus 26 kg. So this is our answer. Good. So this was problem number 7. Let's go to problem number 8. So we are given two energy levels. Okay. This they are calling as 2p3 by 2. 2p3 by 2. The other one is 2s1 by 2. And now we are asked about how many permitted transitions, right? How many permitted transitions? So for 2p3 by 2, for 2p3 by 2, j is 3 by 2 and here j is 1 by 2. Okay, so let us write for 2p3 by 2, our mj, this will be from, this goes from minus j to plus j, right? So minus j plus 1 minus j plus 2, which is yes, and then plus j. For 2s 1 by 2, mj will be minus half and plus half, just the two terms. So now let's talk about selection rule. So selection rule is delta mj is equals to 0 or plus minus 1, but if delta j is 0, delta mj is equals to 0 is not allowed. So that is not allowed. So this is the selection rule. This is the selection rule. Okay. So let us write all these values. Okay. So let us write for 2p 3 by 2, our mj will be minus 3 by 2. Okay, let's write from highest to lowest. So 3 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2. For 2s half, mj's will be minus 1 by 2. Again, let's write from biggest to smallest. So half and minus half, these are the only two. Now let's draw transitions. So when mj is 3 by 2, okay, when mj is 3 by 2, can it go to, so what is the delta here in this one? So delta mj, which is 3 by 2 minus 1 by 2 is 1. So this is possible. Okay, so this transition is possible. Okay, what about 3 by 2 and minus 1 by 2? So this becomes 3 by 2 minus of minus 1 by 2, which becomes 3 by 2 plus 1 by 2, which becomes 2. So this one is not possible. Okay, so this one is not possible. For 1 by 2, 1 by 2 minus 1 by 2 is 0, and here delta j is not 0. So this transition is possible, and this transition 1 by 2 minus of minus 1 by 2 will become plus 1 by 2, so this will become 1. So this is also allowed. Similarly for minus 1 by 2, with this it will become minus 1, and with this it will become 0. So both of them are also allowed. For minus 3 by 2, so this one is allowed because here delta time j is 1, and here with this one delta time j is 2, so again this one is not allowed. So 2 transitions out of 8 are not allowed. So total transitions 8, not allowed transitions are 2, therefore possible transitions is 6. So yeah, option B. Okay. So here we were given two spectroscopic terms, 2p 3 by 2 and 2s 1 by 2. So for 2p 3 by 2, we can clearly see that the subscript is 3 by 2. So this means that j is 3 by 2, and your subscript is half. So here j will be half. Another thing that we know is that mj, it goes from minus j and then it keeps increasing by 1 and goes all the way up to plus j. Therefore we can write the value of magnetic quantum number mj for both these terms, and we get 4 mj values for 2p3 by 2 and 2 mj values for 2s1 by 2. Having done that, we also have one selection rule that for any transition delta mj, which is the difference in the value of mj, that has to be either 0, plus 1 or minus 1. And there is another rule that if delta j is 0, then delta mj is equals to 0 is not allowed. Okay, so but if delta j is 0, but this is okay, this is not valid in this case. Right? This is not valid in this case because here you can see delta j 3 by 2 minus 1 by 2 is half, is 1. Therefore this is not valid. Therefore we just map out all the possible transitions, and which are 8, and then we remove the not allowed transitions which are blocked by selection rule, which is 2, and therefore we get possible transitions as 6. Okay, That was a problem based on selection rules when we have transition from one state to other. Let's do the next one, which will be question number 9. Okay, so this is our next problem. And we are given several effects. Okay, and we have to identify the one in which there is splitting of spectral lines. So splitting of spectral lines due to electric field. Due to electric field. Okay. So this was discussed in the class, and this is a standard information that this is known as Stark effect. Now here this is Zeeman effect, right? This is also Zeeman effect. So from the name itself you can deduce that both of them are happening because of magnetic field. So there is splitting of spectral lines in both cases because of magnetic field. So here we have Stark effect, this is electric field, and this is the correct answer. Now what is Paschen-Bach effect? So this is a little less known. Okay, some of you may not have heard of it. Okay, but this is a phenomena, and it also happens because of magnetic field. Okay, so what it does is, let me write here. So this Paschen-Bach effect is so strong magnetic field disrupts the coupling between atoms orbital in angular momentum. Okay, so this is Paschen-Mag effect, and then because of this, what happens is, so this leads to different pattern of spectral line splitting compared to the weaker field Zeeman effect. Okay, so this happens because of strong magnetic field. Okay, strong magnetic field, Paschen-Mag effect. And normal anomalous Zeeman effect happens because of moderate and weak magnetic field. So the only effect in this one that does not happen because of magnetic field but happens because of electric field, the splitting of spectral lines, is Zeeman effect. Okay, so therefore that is the correct answer. So let's write next problem. Let's write the next problem. Question number 10. Okay, so this is question 10. Question number 10. Yeah. So this is talking about an atom that has spin I equals to 3, and we are given two levels, 2d3 by 2 and 2p half. And the question asks us to find the expected number of components in the hyperfine structure of the corresponding spectral line. Okay. So we are given I is equals to 3. Therefore we can write f as, it will go from j plus I all the way up to j minus I. Okay. So for 2d 3 by 2, our f, okay, first of all j is 3 by 2, and for 2p 1 by 2, j is 1 by 2. Right? So this much we know. Now let us write f, the possible f. So let's write for 2d 3 by 2 first. For 2d 3 by 2, j is 3 by 2. So f will be, so 3 by 2 plus 3, 6 by 2, 9 by 2. So this will be 9 by 2. Then we subtract 1, 7 by 2. And 3 minus 3 by 2 is 6 minus 3 by 2. So 3 by 2. So we go all the way up to 3 by 2. Yeah, like this. For okay, for 2p1 by 2. So here j is 1 by 2. So 3 plus 1 by 2 is 7 by 2. And 3 minus 1 by 2 is 5 by 2. Okay. That's it. So only two possible values of f. Now, what is the selection rule? Okay, so this is the selection rule. Okay, so what we can do is we can draw these energy levels. So let's first draw 2d 3 by 2. Let's say this is the energy level, and we can have 4 components. Okay, we can have these 4 components. And these are different values of f. 9 by 2, 7 by 2, 5 by 2 and 3 by 2. Similarly, we can do for 2p half. And it will be split only in two lines. This is okay, like this. And this will be for f is equals to 7 by 2 and f is equals to 5 by 2. Okay, like this. So let's start with the topmost one, f is equals to 9 by 2, and 9 by 2 minus 7 by 2, that is just 1, so this is allowed, and minus 5 by 2, so this is 2, therefore this is not allowed. Okay, so only one transition is allowed, which is this. Now for 7 by 2, so minus 7 by 2 is 0 and minus 5 by 2 is 1. So this is allowed and this is allowed. So both of them are allowed. So this is allowed and this is allowed. So both of them are allowed. Here minus 7 by 2 is minus 1 and minus 5 by 2 is 0. So again both are allowed. Finally, so minus 7 by 2 will give us minus 2 and minus 5 by 2 will give us minus 1. So only one transition is allowed. Okay, so total 1, 2, 3, 4, 5 and 6 transitions are possible. Okay, and the transitions which are not allowed, so one is this one. Okay, this is not allowed. And the other is this one. This is also not allowed. Therefore, we get six spectral lines as shown above. Okay, so the correct option is 6. Okay, so this was a problem based on hyperfine structure. Okay. We are given an atom, it has spin I is equals to 3 and it has two levels, 2d3 by 2 and 2p1 by 2. Now when we couple the nuclear spin I, we get I plus j as f. Okay, so this is the coupling scheme, and now value of f can go from I plus j to the mod of I minus j. Okay, therefore for both the levels we can have different values of f, just like we have calculated here. So four values of f for 2d3 by 2 and two values of f for 2p half. Then we can draw these spectral lines using the energy levels and selection rule. So like this we have drawn different f levels for 2d3 by 2 and 2p half, and then we check if delta f is 0, +1 or -1, then the transition is allowed. If delta f is, for example, +2 or -2 or anything else, then the transition is not allowed. So from 8 in total, 2 are not allowed. So that leaves us with only 6 possible transitions. So this was question number 10. Let's do one last problem and then I'll call it a day for today because it's almost time. This will be question 11, I guess. Yes. Okay. So again, this question is for a carbon monoxide molecule. Excuse me. For a carbon monoxide molecule, let R be the bond length, I be the moment of inertia, and let M be the reduced mass. Okay, let M be the reduced mass. Then the bond length R will be so here are our options. Okay, so this is the last question for today, and you can see we are given that R is the bond length, okay, I is moment of inertia, and M is reduced mass, and then we have to find the bond length R in terms of I and T. Okay, let's say this is C, let's say this is O, C, O, let's select this thing. Okay, then this is R, and this is what we are required to calculate, that what will be the bond length. Now let this be MC and this be MO. So we defined the reduced mass mu. In this case it is given as M. So M is the reduced mass, and this we know that we can find like this. Okay, good. So now we know that if M is the reduced mass of CO and R is equals to bond length, then moment of inertia moment of inertia okay, I is given as mr squared. Okay, so rearranging, we get r squared is I over m, or r is plus minus I over m, and because this is a distance, this is a length, therefore it cannot be negative. So finally r is equals to under root I over m. Option A. Okay, so once we know reduced mass of a molecule and its moment of inertia, here if you know the reduced mass and moment of inertia, then the bond length is simply square root of the ratio of 2. So I by m, and then take their square root, so we will get bond length. Okay, so this was very simple problem, and here is how you can compute the reduced mass in case it is not given. So in case it is not given, then in case the mass of individual atoms is given, then this will simply becomes mc plus mo divided by mcmo. Okay, so this is another way of writing it. Okay, so yeah, that's all for today. We solved few problems based on the week 9's lectures. We covered hyperfine structure, some problems on molecular physics, some problems on spectroscopic terms, the transitions, transition rules. Okay, so bunch of problems, and I hope these videos are helpful. Okay, sorry for that. Okay, so I'll upload this on YouTube, and if you have any doubts, you can ask in the comments or post a message in the forums on the NPTEL website, and then I'll try to respond as quickly as possible. Okay, thanks for watching. See you next Saturday from 3 to 5. Bye bye.